Welcome, everyone. Thanks for joining us at 5:30 on a Thursday evening to talk about in-depth topics on distributed databases. So if that doesn't interest you, then you're in the wrong place. But welcome, and thanks for joining us. My name is Adam Levin. This is Sharon, Dashet. And we're going to do a little deep dive into Cloud Spanner and Cloud Bigtable. So before we get started, just a friendly reminder to please fill out surveys. We love feedback. And so those will open 20 minutes into the session. As I mentioned, my name is Adam. I'm a product marketer based out of San Francisco. Sharon is a big data specialist based out of Tel Aviv. So we figured London was the most convenient place to get together, have a cup of coffee, and talk about databases. What we're going to do today is talk a little bit about why manage databases. I promise to make that brief, and then we'll get into the depths of Spanner, how it works, Bigtable, how it works. We'll do a little demo, and then we will talk a little bit about some of the migration and modernization options, particularly to Bigtable. And then if we have the time at the end, we can do some Q&A. So let's get going. And so I wouldn't, a discussion on Spanner and Bigtable wouldn't be complete without a little bit of a history discussion to begin with. So Google as a company has been building tools and services that help people build their in their lives for as long as Google has been around. One of the things that enables that is data. And data and the infrastructure to manage that data underpins all of which Google does. And so Google has been tackling big data problems for 15 years. Some of those innovations have resulted in famous open source projects like MapReduce, HBase, things like that. And then they've also resulted in commercial products that you have access to go build on within Google Cloud. But it all comes down to managing data at scale. And along the way, we've learned a few important lessons. So before we talk a little bit about those important lessons, a quick story. So when Bigtable was first created and first produced, it was sort of handed over to developers within Google to manage themselves and run themselves. And so a developer had to spend time maintaining and managing Bigtable and then building the application that ran on top of that. And what the Bigtable team soon discovered was that that wasn't efficient. All of these developers were spending their time operating this thing instead of adding business value and building code on Bigtable. And so they decided to build a managed platform that developers could then access and build on top of, but the management would be centralized. And this had two big effects. One was that developers could just build and focus on adding business value, but also for the team that was managing this thing centrally, they were able to discover bugs and edge cases and solve those at a much sort of higher rate before they became bigger issues. So a challenge discovered by one person over here was solved for someone over here. And so that was a really big advantage. And so the same lesson holds true for all companies building and running applications in the cloud. So by relying on managed services, you're able to reduce your operational overhead and toil. And instead of worrying about availability, upgrades, security, hardware patching, you can let a managed service help you achieve that for you. And then you can focus your energy on higher priority work, like adding business value. Now, that's not the only lesson we've learned in managing data at scale. There's a few other things, but the overarching point is to let specialized systems that operate at scale manage that data so you can focus on adding business value. So let's take a quick step back. There are many databases out there. dbengines.com, if you're familiar with them, tracks 343 as of a couple of months ago. Each line on this represents one of those databases, and I actually got tired of clicking to load them up, so I don't even think this is all 343. And so you have lots of choices to choose from. In addition, Gartner is saying that by 2022, 75% of all databases will be deployed or migrated to a cloud platform. And so managing infrastructure and the databases that they run on isn't a core differentiator for most companies. And so whenever possible, you want to take advantage of a managed platform. And so then your database choice comes down to what your application needs, what your industry is, and really what your cloud provider offers. And on GCP, we have a wide range of databases, both systems that are built and managed by Google. We're going to talk about Spanner and Bigtable in 2 seconds. But then I also wanted to point out that we do have a range of options that are provided by partners, as well as you can really run anything you want on GCE, which you see over on the far side. And so today we're going to focus on Cloud Spanner and Cloud Bigtable. So a few minutes in, let's dive into Cloud Spanner. And we have to start with a discussion on what's tricky with databases. And so Cloud Spanner addresses these challenges with a combination of scalability, manageability, high availability, transactions, and complex query. That's a lot of ands. I say a combination because there are other systems out there that address this in sort of an or fashion. So it's scale, or transactions, or replication, or high availability. But with Cloud Spanner, what we're doing is we've created an and statement. We're taking the best aspects of relational databases and distributed databases and combining them together. It's not to say that like the 30 years of features that are in existing relational databases all exist in Cloud Spanner, but we've combined relational semantics with horizontal scale. And as we go deeper and deeper, we have to start understanding what the differences are between Cloud Spanner and traditional relational databases. And one is that the application is in control of its data when you use Cloud Spanner. And so, traditional DBs have a lot of complexity. They have stored procedures and other business logic inside the database engine. Cloud Spanner, that's all pushed to the application. And that allows Cloud Spanner to scale really well. And so Sharon is going to talk through how Cloud Spanner works and how it's different. And it's really helpful to understand how it's built and how it works to understand how to approach building on it.
Thank you, Adam. So, sorry. So to reiterate what Adam mentioned about having the best of both worlds, so Spanner is both relational and also highly scalable as NoSQL databases, right? So I have a personal story I would like to share with you. I started in the late 90s as an Oracle and SQL Server DBA. And back in the days, even as a developer who was not part of the production team, we had to do a lot of administration tasks and maintenance and many stuff that were part of your source control, like exchanging partition, like vacuuming, rebuilding indexes, and some of the stuff really is like house chores, right? You would like to concentrate on your business logic. So we did like 60% of administration and 40% of business logic. But I think the worst was the inability to scale whenever we wanted to introduce a new workload, whenever there was a new customer that joined the production system. So whenever we needed to scale, there were very expensive hardware involved, long-term upgrade plans, and this was a hassle and tempered both innovation and both the business. And who can ever afford it would buy a very expensive appliance or use a shared storage system, like some of you know. I will not mention names. So moving forward to around 2010, when the big data disruption happened and Hadoop came and a lot of NoSQL and columnar databases based on commodity server were coming to the market, I remember me and my data team sitting for coffee, And we were thinking, what if we can have both? So both relational ANSI SQL system that can scale like NoSQL. And it looked like a dream, really. But when we heard about Spanner a few years later in a Google conference like this, we were very pleased. So this is like a full circle for me. And what are the building blocks of Spanner that make it both scalable, highly available, and both relational? So these are the Google network. For those of you who don't know, we have a global backbone private network, very reliable and fast. The true time, and true time is our global synchronized clock, and we are going to speak about it later to understand how can true time make us both relational and scalable. And we made some optimization to the Paxos algorithm, the famous Paxos algorithm for two-phase commit. And on top of that, we have some automatic rebalances of the shards of the table. So these all can explain why Spanner is high available, performant, scalable, and relational. So every big data talk has the CAP theorem in it, so we are not different here. So in a distributed system, we cannot have all three guarantees of partition tolerance, availability, and consistency. So the traditional relational system would sacrifice availability for the sake of consistency. And the NoSQL system will sacrifice consistency for availability. But what about Spanner? Do we break the CAP theorem? The answer is no, no, no. We don't break it, but we minimize the chance of partition, of networking partition, because we have this highly reliable, redundant network. So we can have very high SLA, but if we have to sacrifice something, we will sacrifice availability because this is a relational system. And a fun fact, Eric Brewer, who created the CAP theorem, is working in Google, and he has written an article about true time, Spanner, and the CAP theorem, if you would like to check it out. So, okay. So what we see here is a regional instance. In Spanner, we have two configurations, one regional and one multi-regional. The regional is under 4 nines SLA, and recently we announced that even with one node or two nodes, we can have 4 nines SLA, and this is a big improvement. So you can start small with Spanner and do a POC, and then you can scale out. And what you see here is something that is very interesting. We have a separation between the storage and compute. So a node in Spanner is a unit of throughput and compute. It does not have any storage. The storage is elsewhere. It's distributed. And every one of the Spanner instances can have more than one database. We can have up to 100 database sharing the same configuration and the instance to enjoy the same resources. But in Spanner, we don't, as far as multi-tenancy, we usually do not design a database per tenant. We use the primary key for that. So databases are for sharing the same resources. In a multi-region configuration, we have 3 types of replicas. In the main region, in this example, you see a Spanner across 3 continents. So the US is the main region in this example. We have what we call read-write replicas. And these are replicas we can write into. And we have something that is called a witness replica. So this will ensure us a quorum even if the write replica is gone. In addition to that, in the other regions, we have read replicas. So this is very performant. The readers can read close to their zone, and we have this global high availability. And often, when we speak about spanner, we speak about external consistency. And external consistency means that the system behaves as if all transactions were executed sequentially, even though Cloud Spanner actually ran them across multiple servers. So it acts like a one-node database, but it is a distributed system. So this is twofold. This is due to the very fast network and our synchronous replication and the customization we made to the Paxos protocol. And the other factor is true time. So often true time is mentioned as one of the building blocks and what makes Spanner ticks. And pun intended here. Because true time is a globally synchronized clock. And in true time, in each one of the zones of Spanner, we have combination of both GPS and atomic clock. Each one of these clock types are compensating for the other's failures. And in addition to that, we bring into the timestamp, we attach to every write and read uncertainties of the network. So even if we synchronize every 30 seconds the local time and the reference time, we can have drifts in the local clock, and we have uncertainty that can be as much as 2 milliseconds. And this is used as an epsilon as part of the formula that Spanner is comprising when it has to attach the timestamp to the transaction. So why am I telling you all this? It sounds complicated. So this is how Spanner makes sure that one timestamp does not overlap with the other. And this is what makes this sequential. So there are no collision, and the readers can read multi-versions. So it is also a multi-version database, and the readers can read a very consistent version of the data without holding locks. And this is rather revolutionary in distributed system. And on top of the true time and the replication, we have automatic table split. So the keys in Spanner are ordered and split amongst the nodes of the cluster in what we call key ranges or splits. So each node can have one or more split of the table. In our example of 3 nodes, so each node will have three splits, and we will get back into splits. And every split has one leader that is allowed to write into the split and 2 replicas. So this explains why we are so scalable, performant, and highly available, because we have 3 replicas of each data unit. Okay, so we talked about the wonders of Spanner, but at the end of the day, this is a distributed system with network in between. So we do have some best practices around primary key, around child tables, and around indexes you need to keep in mind when you start your adventure on Spanner. First, how do you keep parent-child relationship? So you heard from Adam, we don't have many knobs to turn. It is not like the classic relational system with the triggers and the integrity constraint. But if you do want to collocate in the same physical node the child and the parent key, you should use the interleave keyword, like in this example. So in this example, if we interleave the foreign key table, the singers, with the parent, the albums, they will be collocated together on disk. So this is when we don't use the interleave keyword. We have 2 separate tables, the singers and the albums. But if we do use the interleave, it will look like that. So we have collocation of the foreign key, the albums, with the singer. And we have some type of indexes in Spanner. Automatically, every primary key will have a unique index. We also have the ability to create independent interleaved index or non-interleaved index. We have other types of indexes, like null-filtered indexes. These are indexes without nulls, because by default, nulls are getting indexed. And we also have some covering index, so whoever worked with MS SQL know the term. So covering index is helping us to prevent lookups to the base table when this is applicable. And remember the split we talked in the scalability chapter. So we used an example of monolithically increasing primary key, and in fact, this is an anti-pattern, because we don't encourage this. By default, the last, in a monotonically increasing primary key, the last records will be appended to only one node, and this is split number 8. So we don't want one leader to accept all hotness from the new records. So this is why it is recommended to distribute the keys by using a unique ID, or by using some field promotion or salting, or some type of mechanism that we will have even distribution of the split. And finally, we have some new features in Spanner. We talked about the 1 and 2 node guarantees, the SLA. We have some new graphs in our monitoring system, in the console. We introduced JDBC driver. We introduced support in Hibernate, and some more security control. And with that, let's get back to Adam to speak about Bigtable.
Great. So I told you that we had a lot to cover, and it's sort of a whirlwind deep dive. So moving right on from Spanner to Cloud Bigtable. And so Cloud Bigtable is our scalable, high throughput, low latency data store. And so it's a, if you're familiar with the types of NoSQL databases, it's a wide column or key value data store. It's really good for low latency, random data access. It's often sort of partnered with BigQuery for a lot of workloads, particularly around real-time analytics, doing machine learning and AI on top of lots of, let's just say log data. And the really nice thing about it is that performance scales linearly as you add nodes, and that's a completely online operation. So same thing is true with Spanner, where any sort of scaling procedure or any sort of, with Spanner schema change is all online. So there's no such thing as planned downtime for these databases. One other thing to note about Bigtable is that it's fully compatible with the HBase client. So if you have HBase that you're running yourself, it's relatively straightforward to move to Bigtable and use that. One use case that we'll talk about a little bit later is also moving from Cassandra to Cloud Bigtable, because those are can be similar data models and similar use cases. One thing to note about Cloud Bigtable is that it's fairly well integrated with the rest of the GCP ecosystem. So you can actually query directly from BigQuery into Bigtable. It's integrated with Dataproc and Dataflow. And then most importantly, it's integrated with TensorFlow. And so there are a lot of people building ML models on top of Bigtable and using that to sort of process and then serve personalization data. Which takes us to the most common use case for Bigtable are things that fall under a very broad umbrella of personalization. And so this is really high throughput reads, low latency writes, and that integration where you are doing predictions on clickstream data, or you're wanting to create a unique user experience based on actions. And you can sort of use all that Bigtable offers to do this. And we see lots of customers doing this today. The linear scalability of Bigtable makes it sort of very sensible for ad tech, fintech, gaming, IoT, and other use cases where you just have tons of data coming in and you need a place to put it and then access it later. And so, as I mentioned, Bigtable is often used with BigQuery, and this is sort of the very high level architecture diagram that we see for this sort of wide umbrella of personalization workloads. And so that's just a quick run through of Bigtable. Now Sharon's going to talk a little bit about what's going on under the hood with Bigtable and how it's able to achieve such throughput and performance.
Thank you, Adam. So no personal story here, but we have a very nice demo coming. And a little bit about the terminology around the Bigtable. We have an instance, and an instance is a container of cluster. We can have up to 4 clusters, and we have them in various zones and regions. So each one of these clusters is attached to a zone. And we have nodes that are also called tablet servers. We are going to speak about what a tablet is. And you can attach a storage that is either SSD or HDD. And of course, for production use cases, we prefer SSD. It has a few millisecond latency. But there are some use cases when you don't care about latency as much as the cost. So you can use HDD as well. And in Bigtable, as in Spanner, the nodes are a unit of compute and throughput. They also does not have storage of their own because the storage is separated from the compute, and we will speak about it later. And what is very nice about Bigtable is that we can scale easily by adding more nodes. So each node we add to the cluster is roughly about 10,000 QPS, so you can scale up and down according to your requirement, your throughput, your performance, or your cost planning. And you can see here, it scales very easily. And what we see here, so we talked about the nodes are separated from the storage. But we have another wonderful thing happening. This is automatic rebalances. So every one of the nodes is a throughput unit that is responsible for writing and reading to the storage of the Bigtable system. But once we see one of these nodes is more loaded than the other, we can, the routing layer of Bigtable can automatically place the shard in another node that is less busy. Each one of these shards is called tablet, and this is why the nodes are also called tablet server. And you can think of it as like a logical unit handled by only one node. So those of you who handle Cassandra or HBase, it's very similar to regions or partitions. And a little bit about data modeling. So in Spanner, we spoke about, we have some best practices everyone wants to know and needs to know. In Bigtable, this is mostly around modeling the key. So modeling the key, because you heard from Adam, this is a key value system. So the atomicity of the transaction is in the context of one row. It does not cross rows. So this is why it's very important to model the key properly. So the only index in Bigtable is the key index. So if you need additional indexes, you would probably create additional tables or use some of the server-based filtering that will happen after you retrieve the blocks from the storage. And what you see here is the column families. Column families are a way to group together physically columns that have a common characteristic. So you can collocate them together physically. And with each column family, we have one or more columns. And the system is very sparse. What do I mean? That you can have, in one row, you can have 100 cells, and in the other, you can have only 50 cells. So you don't pay for what you don't write. Each one of these cells has multiple dimension. So the cell is per key, it's per column family, it's per column, but it's also versioned. So you can do upsert and write versions in the same cell, and there will be a garbage collection that will collect the older version, and you can play with the configuration and decide that you want to keep all version, or you can keep only the last version. And in addition to that, you can also configure time to live, TTL, in the column level family to control historical data, aging out. So we see many systems like that in the ATEC, in the monitoring. So they use both the garbage collection configuration and the TTL. And this is one of the most important design tasks you will have to do per a table in Bigtable. This is to decide about the key. So we will try to avoid keys that create hotspot. That, for example, we have an IoT system in this example, and we would like to monitor metrics of a device like memory, CPU, storage. In this example, if we model the key to be around only memory usage across all the devices, we will create a hotspot. So adding the timestamp can alleviate some of this problem, but it will also introduce another problem of sequential writes that can also create hotspot. So what we propose here is doing field promotion by adding the user in this example is the device, to the key. So I learned from many customers that when they chose the wrong key, the performance was not as expected, and when they did the rethinking and designed the keys as these best practices, they got a few millisecond latency as expected. And this just summarizes what we said so far, but what we haven't spoken about is some best practices around the size of a single cell and the size of a single table. So we recommend the cell to be not more than 10 megabytes, and the row not to be more than 100 megabytes. So if you have a very large row, you will start to see some warning in our monitoring system, as we will show you later. And these are the common API operation in Bigtable, and most used are put and get to write and read a single key. Also very popular is the range scan. So if we would like to create a monitoring system, time-based, or anything else that is time series, we can use a range scan to read more than one key in the same API call in a very performant manner. And this is about writes. So reads are very fast in Bigtable, but writes are even faster. And this is because every one of the mutation, the updates or the rows in Bigtable is being written first into memory for consumption, and only then it is flashed to disk in the form of what we call SS table. So SS table is the most optimized way to keep the keys ordered and the values in the same place. And we also have a commit log. So every row we write in Bigtable is being written first to a commit log to assure us that even if the node crashes, we still can recover from the transaction. And finally, just before the demo, bear with us because the demo will be interesting. This is about monitoring. So monitoring in Bigtable can be done by using the console. And in the console, we have very useful graph for CPU, for storage, for throughput. We can also use Stackdriver, and Stackdriver is the Uber monitoring and tracing, auditing suite we use for all GCP products. And one of our customers, you may know them, Spotify, created an open source project for auto-scaling Bigtable programmatically based on metrics from Stackdriver. So whenever they can detect a node that is too large as far as storage or CPU, they will auto-scale the cluster in an automatic manner. So this is the project by Spotify. And we can also add some client-side monitoring by using open sensors, for example. And finally, we have Key Visualizer. And this is a very interesting piece of engineering. This is a heat map that will show us in a visual manner a lot of dimension of performance in the big table cluster. So horizontally, we can see the timeline, so we can see summaries over time of CPU, of reads and writes, and rows distribution. And vertically, we can see the entire key schema by prefix. So if the tool can make sense of the primary of the key, you can see it as a hierarchy of prefixes in the vertical axis. And a heat map is a heat map, so all the cold values are dark, and all the hot values will be very bright, like luminine bright. These are some of the common patterns we can see in Key Visualizer. For example, you can see a periodical usage, so the entire key schema is affected at once by something that is happening, normally a batch, MapReduce, or Apache Beam. And the diagonal pattern you see here on the bottom right is also interesting. It's indicative of a sequential scan or write, usually, again, by a MapReduce or one of the processing frameworks. So we can move to the demo. But first, I have to tell you something about the demo. In the demo scenario, we are going to walk you through how to monitor, troubleshoot, pinpoint performance issue in the cluster, and we are going to also demonstrate how to scale the cluster and the effect of scaling the cluster. So we have an event table, and the event table has time-based trading event of a trading platform. It has 4 kilobyte average row size, and we begin with 6-node cluster. In this scenario, the trading company decided to start with an historical backfill. So they would fill the cluster with some historical data before it becomes production. And when it becomes production ready, they will add replication for high availability and load balancing. They will add application profile. They will have an Angular real-time UI, and they will have streaming. But in our scenario, we are focused at the historical backfill. And we have some readers in the system, data scientists and data engineer, that starting to train the data to do some prediction and time-based analysis. So they're complaining about slowdown and timeout, and we wanted to know what happened. So we took a recording of the system after we asked the reader to stop reading so we can see what is happening in the cluster. So without further ado, let's look at the recording. What we see that the cluster is starting to fill up with the historical data, and we can see we have 6 nodes and relatively high CPU. So we go straight to the monitoring pane to see what is happening. We can see we have very, very high peaks of CPU above the recommended threshold. And we can see that these spikes are coming from writes, not from reads. So we know something is related to writes. And we can also see this high throughput that is in correlation to the peaks we saw. And we are using now Key Visualizer. We will use Key Visualizer to understand more. So usually you will start with the monitoring console, and when we would like to have more insight, like what is happening in the key space, whether we have warning about large rows, what is hot and what is not, we go to Key Visualizer. So we can go to Key Visualizer now. We can open Key Visualizer directly from Stackdriver, from the resources menu. And we have both daily scan or hourly scan of the system. We go to the last hourly scan. What we see here is the ops metrics, is the aggregation of reads and writes per key. And we see a periodical pattern that is coming strictly from the CPU of writes, from the writes. And we can also see very high latency of a few seconds, which is not expected. So this is what we will try to tackle, to lower this latency that can explain the peaks we saw in the CPU. And we can also look at the time-based summary in the horizontal axis, and on the key space in the vertical axis. We have another metrics showing the distribution of rows amongst the buckets of the keys. So Key Visualizer will try to divide in an even manner the rows of the table between what they call key buckets. And these are mainly for visualization. In this example, we don't have an even distribution yet, because this is a relatively new cluster, so we don't have the entire key space yet. So this is rather normal. We happen to know that we have Dataflow, our managed version of Apache Beam, ingesting the historical backfill. So this is most certainly the problem, because we saw this is coming from writes. And we also know that we have an Airflow, or most precisely our managed version of Airflow, Composer, that is orchestrating the ingestion. So let's go to Composer, or to the Airflow UI. And we can pick the last ingestion task from the Airflow UI to see what is the name of the data flow job. And the purpose is to take the name and to go to the Dataflow UI to correlate what we see there with what we have seen so far. So this is the name of the Dataflow job. This is the Dataflow UI. We go to the Dataflow job, and we see a throughput that is matching what we saw in the UI of Bigtable. And if we go to the last transformation stage, we can see also the number of rows we write and the storage we save in every one of these ingestion jobs. So this is pretty heavy, and it can explain why the clients are imposing too much stress on the server. So our conclusion at the end of all of that is that we need to scale the cluster. We need to scale Bigtable, to be able to soak all this pressure from the clients coming from Dataflow. And this is what we have done. We scaled the cluster from 6 to 12. And after about 20 minutes, we started to see an improvement, and we started to see that the CPU went lower, throughput went higher, and the reader started to work with the system without any complaint. And this was done very easily, because scaling in Bigtable can be done programmatically, can be done by the UI or by the command line. So let's look at the recording of the system after we fix it. And we can see in the graph that the CPU went down, and in correlation to the CPU being back to normal below the recommended threshold, we go to the throughput graph, and we see throughput went high. So we probably can have more frequent writes now and more workloads in the cluster. And if we look in a perspective of 4 days, this will become even more apparent how the scale made such an effect, and we have now room to breathe in the cluster. And what is happening in Key Visualizer now? So again, we go to the last hourly scan. We don't expect this periodical pattern to go away, because we are still ingesting. But we do expect latency to go down. So let's look at the latency. So the max latency should be around few milliseconds, and it is around few milliseconds. So now we are not choking, and this is what we expect of the system. And this was done with only a few minutes of troubleshooting and a few clicks. And this concludes the demo. And we have a few more things to say about integration in Bigtable and migration path. So Bigtable inspired all the system you see here, and most noticeably HBase, which is one of the major part of the Hadoop ecosystem, and also Cassandra, which was open sourced by Facebook on 2010. And Cassandra was inspired by more than one system, but mainly from Bigtable. So you must be wondering, why would we want to move from system like Cassandra, for example, to Bigtable? So the main reason has to do with the operational burden, because I myself manage Cassandra, and it has a lot to do with tuning consistency level, of tuning meme table, of tuning Bloom filter. So we don't have all this burden in Bigtable, and we have a very low touch replication, and we don't have to deal with a lot of discovery, topology of the network, and you can scale up and down very easily and save cost according to your throughput and performance. And finally, we have interesting platform integration in GCP, like Adam showed you. For example, in most of the recommendation and personalization products, we will use a combination of BigQuery and Bigtable. And all this integration make this even more powerful. So I think we concluded before time. Yeah, so you can go home. Thank you.
Thank you.